Welcome back to the HMEI Faculty Seminar Series. It is fall of 24. We got started a little late. We skipped September because why not? So it is really my pleasure to get the seminar series started with Christos Maravelias, who is the Anderson Family Professor in Energy and the Environment. He's also a professor in Chemical and Biological Engineering and at the Andlinger Center for Energy and the Environment. With all those roles, he also serves as chair of the Chemical and Biological Engineering Department. And last year, I got to know Christos quite well. We sat on the C3 and spent our Mondays and Thursdays together. Christos in his career has won a number of awards, has been recognized for a number of things, including this current year receiving the Sustainable Engineering Forum Research Award from the American Institute of Chemical Engineers. Christos received his PhD in chemical engineering from Carnegie Mellon University. Prior to that, received a master's in operational research from the London School of Economics and Political Science, and has his diploma in chemical engineering from the National Technical University in Athens. Christos studies a lot of work on theory and modeling to optimize problems in chemistry and energy processes in general. And specifically on chemical energy production, scheduling and planning, and supply chain optimization. And I think as we will hear today, a bit on energy systems modeling and thinking as a system on renewable energies. And as we think about this energy transition that we've undertaken, I think it's important to have a systems approach, and very excited to hear from Christos. So thank you, Christos.
Thank you, Gabe, for the very nice introduction and also the invitation to be here. I'm very, very excited to be presenting our work today. So in this audience, I don't have to motivate too much why we would like to study renewable energy technologies. Many years ago, we would have added here also due to national security and also increasing oil prices, but I would, since 10, 15 years ago, I was always arguing that this is really environmental concerns that may kind of necessitate that we study this type of energy systems and technologies. And of course, this has been recognized by a wide range of scientists and engineers, and there is a lot of research going into the development of these new technologies, starting from what I would say old renewables, for example, photovoltaic or wind, to solar fuels, biofuels, and so on and so forth. But despite this wealth of research in this space, I would also argue that there are many, many open questions and here I have listed some of them. For example, if we go beyond light vehicles, would it make sense to try to electrify or continue using liquid fuels? And then if we choose, let's say, to go with biofuels, which platform is better to convert biomass to a form of liquid fuel, and so on and so forth. So my main kind of message today is that systems engineering help us think about this type of questions, frame these questions, sometimes give some answers, but even understanding is important if we don't obtain definite answers. And ultimately, we would like to use these insights to guide future research efforts. So also, I think in our group, we spend a lot of time thinking about the methods that are required, the new methods that are required to address the new type of problems. But I won't be focusing on this today. I'll just maybe have a couple of slides to highlight some of this method development. So this is the outline of my talk. Because of the very wide background in the audience, I've chosen to talk about kind of 3 different vignettes. So some of my slides are a little bit dense. But again, I chose to give 3 different examples after I have introduced the methods that we use, right? Some preliminaries about what I'm calling here optimization-based process synthesis. Before I start with the preliminaries, I'll just say that in general, systems engineering can address many different types of questions. So it can be divided in terms of areas, but also it can be divided in terms of types of questions. And I would say at a high level, there are three types of questions that we are trying to address. Design questions, so these are questions that concern very long-term horizons, right? How would we design a new facility that utilizes biomass? So that's a 30-year kind of decision. Then there are operational questions. How do we operate a system? This, we're talking about days to weeks, maybe to months. And then finally, if we're thinking about an electric grid, we have control problems, right? And here we're talking about seconds, right? Seconds and minutes. The decisions have to be made in real time. My talk, for the most part, is going to be based at the first level, which is design, long-term decisions. So how do we design these systems? Traditionally, we have tried to decompose these problems into smaller problems that we are kind of better equipped to address. In chemical engineering, I'll give an example in chemical engineering, but I'm pretty sure that similar examples and similar sequences are present in many other disciplines. So in chemical engineering, we're essentially trying to get some new chemistry and design the system that would allow us to employ this chemistry at large scale. So we start with the heart of the system, as we call, which is where the chemistry happens. We have to decide what type of reactor we're going to employ. So the details here are not important. We make these decisions. Then around that, we will have to make sure that, for example, the feedstocks are not wasted. So we have to recycle them. Or our final products meet some specifications, right? When we go to stores and we buy some plastics or all the everyday products that we use, they have to meet some certain specifications in terms of purity, right? So this next layer of decisions is going to ensure that these specifications are met. And finally, we optimize energy. So this is very intuitive for the engineers or the chemical engineers in the audience. It almost mirrors the curriculum in our undergraduate education, right? We have a reaction engineering course and then separations and then unit operations. This is great. This is very intuitive. It leads to good solutions, but it can also lead to very suboptimal systems. And just to give an example, if we are trying to optimize what happens in this system, we may design the system in such a way that is, yes, optimal from a reaction standpoint, but then this system becomes, or this problem becomes extremely difficult and actually has no good solution. I'll be happy to give examples later. So what's the alternative? And what we use in the group is what we call superstructure optimization. So what I'm showing here, again, it's just a sketch, it's not meant to be fully understood, is a superstructure is a network that contains all the different alternatives that could be designed for a given facility. So not all of these pieces are going to be part of the final solution, but we don't know that at the beginning. So we come up with this structure, which again has all the alternatives. Then we formulate a model. That's one of the two slides that I'll have some equations. This model is an optimization model. So there are some variables here, these x's. These are the variables that we want to find. Maximizing or minimizing a metric of choice. This can be minimize cost, minimize environmental impact, a combination of the two. Many different things can be used for this function. The tricky part and what makes this model very interesting is that this model has binary decisions or Boolean decisions. You can think of them as true or false, right? And if these xb's that are either 0 or 1, and if a variable is true, then it means that the corresponding unit is going to be present in the final structure. And once we have identified the structure, then we can calculate the costs, everything else, the emissions, all the other information that we would like to obtain. Okay, so this seems to be very good, and it's kind of too good to be true, indeed. And the reason is that there are these three very important conditions. So the solution, the optimal solution, has to be embedded in this initial superstructure that we postulate, and this can be challenging. We should be able to develop this model, and this can also be challenging. And you have to be able to solve this model, which is very challenging. So this is where the methods development goes. So in the group, we're spending a lot of time thinking about these three questions. For now, I'm going to assume that we can do all of the three, and I'll just focus on results. Okay. I will also say that in order to be able to solve this model, we have to make some approximations. But this is okay, I would argue, because again, this is very exploratory types of studies. Typically, we collaborate with some colleagues, they provide us with experimental results, then we build these models, and the results of these models are not meant to be used, let's say, to go ahead next year and build a facility. It's more to identify the trade-offs. It's more to understand the drivers of these systems, okay? So typically, we would get some results, we would go back, there's going to be back and forth, and during this process, the models will be improved. Okay. So that's the first kind of small story I want to share is about carbon capture in systems that convert biomass, specifically lignocellulosic biomass. So this is often referred also as second generation biomass. The reason we study this type of biomass is because we do not compete with food. So it's not corn ethanol, essentially, it's everything else that we will not compete for lands with the food sector, but this type of biomass is more difficult to convert to fuels. So, and specifically I have added carbon capture, which is a theme that many people are interested in, but it becomes very complicated, this question. So I'll walk you slowly through this very busy slide. So the gray blocks are the technologies that can be employed to take us from biomass to ethanol. 4 major blocks: pretreatment, hydrolysis, fermentation, and some separations. The block arrows represent flows. The gray, it's carbon flow, so the first thing that we will notice is that if we want to make, let's say, a certain amount of ethanol that contains 1 kilogram of ethanol, then we have to start with significantly more carbon in the feedstock, for reasons that are related to the composition of biomass. So what happens to the remaining carbon? Actually ends up most of it as a carbon dioxide, but there are 3 point sources. There are a source in the fermentation that is very concentrated. It is almost only CO2, and that would suggest that if we capture this stream, it's probably going to be relatively inexpensive to do that. But there are some other streams that contain carbon dioxide, and these are more dilute. So there are multiple ways to do carbon capture in a biorefinery, right? And here are the emissions of carbon dioxide depending on the selection we make. At a very high level, if we don't do anything, then most of it is going to end up 1.96 is going to end up in the atmosphere. And as we're trying to do more capture, less CO2 ends up in the atmosphere, but that the system now is more expensive. And because energy is required to do that capture, actually at some point it might not even make sense to do capture. So that is the question. I won't go through the details, just to illustrate the complexity of the system. And since I have already talked about superstructure, that's a superstructure of a lignocellulosic biorefinery. All these light blue blocks are alternatives for pretreatment. We don't know which one would be optimal. These are alternatives for hydrolysis, alternatives for fermentation. So in an optimal solution, only one of them will be chosen. And what about the capture? Well, the capture is captured in these blocks, in this block. If we choose to do nothing, we just let all CO2 go to the atmosphere, then this would be the configuration. As we try to do more and more, capture this CO2 from more streams, the configuration of the biorefinery changes. So what I'm using here, I'm using a letter code to just simply indicate that there are different ways to design this system, A, B, C, D, E, and E. So let's go directly to the results now. This is a heat map. Every point is the result of a single optimization, okay? So the optimization is going to return a lot of information But at the end, the one metric that we're going to use is the ethanol cost of what we're producing. So we are running an optimization with two important parameters fixed, or with two assumptions, you can say. What's the credit that we would obtain if we were to capture CO2 in a biorefinery? And what is the capacity of this biorefinery? Let me start with the y-axis and why it's important. In engineering, right, and also that's also true in process systems, the capital cost per unit of production goes down as we build bigger systems. That's what we know as economies of scale, right? And in all the systems, again, focusing in chemical engineering, that have been built maybe until the early 2000s, or 99% of the systems, it was always good to build big, right? Because we wanted to exploit economies of scale. So let's say in the Gulf of Texas, the price of a tanker of oil would be the same whether it would end up in a big refinery or a small refinery. So why not build a big refinery, right, to have economy of scale? In these biorefineries, it's a completely different kind of calculation, because as these biorefineries become bigger, the biomass would have to come from farther and farther away. So there is this very interesting trade-off between economies of scale and transportation cost. On the one hand, we would like to make big biorefineries to get the capital economies of scale. On the other hand, we don't want to do that because our average transportation cost would go up, and emissions, right? Because now this biomass, we would have to ship it to the biorefinery from farther away. So that's why capacity is quite important. And then this is obvious, right? As the sequestration credit increases, right now with the Inflation Reduction Act is at 85, it used to be 55 when we published this in 2021. As this credit increases, we would expect to do more and more capture. As we do more capture, we get more credit, the ethanol minimum selling price drops. In other words, the break-even price at which we would have to sell our biofuel, our ethanol, to break even would become lower and lower. So smaller ethanol cost is good. So this is the picture, and I guess the take-home here is the answer always depends on many things. It's not a single answer. So obviously when the sequestration credit is small, we don't do any capture. That was configuration A in the previous slide. As the credit increases, we start doing more and more capture from the fermentation, biogas, flue gas, and biogas. And also there is a dependence with the capacity. These solid black lines show the optimal capacity for the given technology, right? So this is like the trade-off, the best point in terms of capacity when we don't do any capture is a very small biorefinery. But once we do capture, aggressive capture, then the optimal scale is very, very different. So, and this is exactly the same calculation, but here I'm showing another metric, environmental impact. The environmental impact would not change as the cost changes. It would be the same for each one of these different configurations of the biorefinery. Okay, so this was when we're converting biomass to ethanol. And this is typically done microbially. And there is a lot of research actually also on campus in this space. But biomass can be used to do many other things. Again, another busy slide. I'll try to explain at a very high level what we are showing here. So what we are doing in a biorefinery can be microbially converting ethanol through this, microbially converting biomass to ethanol. That's one option. But we can pyrolyze biomass, we can gasify biomass. We can gasify and go to diesel instead of a gasoline component, which is ethanol. We can gasify and go to jet fuel potentially. We can use it for electricity, we can use it for hydrogen. There are many things that we can do with biomass. So here, in what I'm going to be showing next as results, we are trying to do the same thing, the same analysis, but picking the technology that is optimal across a larger palette of technologies. The carbon flows also become a little bit complicated, so I just wanted to very quickly go through this slide, this figure. So we have emissions due to harvesting and transportation, that is not always clear, right? That to grow this biomass and bring it to the biorefinery, we're going to have emissions, right? If we choose to do capture, then we will have sequestration. But when the biomass grows, also sequesters organic carbon, right? So this is also has to be taken into account. And then we produce our product to meet this demand, and then they're going to have emissions by using that product in the case of liquid fuels, but not in the case of electricity. So these are the results for all, not all, most of the technologies that we would like to consider, and the naming convention here is very important. So the first part of this name is the platform: pyrolysis, gasification, fermentation, the three major ways to convert. Now, the second part is, are we going to use, for example, electricity from the grid if we want to do carbon capture? Or we're going to sell electricity. So this is the second part, indicates what our interactions with the grid. The third part is what we make, liquid fuels or liquid fuels or hydrogen. And then finally is how we do capture. The main finding of this study, in some ways, not what we expected, not what we hoped necessarily, but that's what the analysis showed, is that gasification technologies have the highest greenhouse gas mitigation potential, which was a little bit surprising, but that was the case. Okay, and this is the same map, the same heat map that I showed earlier, that shows what's the optimal technology as a function, again, of sequestration, credit, and capacity. Again, the main thing is very different, right? And as I will be showing later, even location sometimes it's very important. So there is no one size fits all, right, in this space. As we change credit and capacity, here, for example, the optimal technology is to gasify without using anything from not buying electricity or hydrogen and producing hydrogen and doing no capture. Again, the credit is very small, so that would be optimal. As the credit increases, we start doing, at the beginning, capturing the CO2 that is only in one stream. This is where it comes from syngas, and then here also from the flue gas. The blue lines indicate, again, the optimal points. So these were the main findings, that gasification to electricity or hydrogen is preferred over any other technology. The insight here is, again, it was not what we were expecting, is that two things. Many times the analysis has been done to energy in the final product. What's the best technology in terms of energy in the final product, ethanol, diesel, gasoline, electricity, without taking into account motor efficiency. The electric motor is much more efficient than a diesel engine. So if we do the analysis in terms of displaced fossil fuel, that's why gasification to electricity is very, very promising, because the electric motor is very efficient. So the same amount of electricity versus liquid fuel, right, it would lead to very different displacement of fossil fuel. And hydrogen is there because we do not emit when we consume it, as opposed to ethanol. Yes?
So these calculations for the sequestration credit, is it a fixed value through your optimization? Do you have considerations where the credit might change?
Not in these results, but we have some recent work where we are considering that. It's just that in this case, so these are like snapshots as if we were to design the biorefinery today. In these other models, we also have now to introduce the possibility of changing our decisions over that horizon because the credit changes or other considerations. You had a question? Okay. So let me now move to this kind of project. Is a continuation of the previous project, which very conveniently had ignored or approximated the spatial aspect of biomass. So what's the motivation here? So we had made some assumptions about the emissions and transportation cost as a function of distance, and that was it. right, in the previous analysis, which is a reasonable first assumption, but as you will see, it does not account for an important aspect. So this becomes now a supply chain problem. Some of you are familiar, but I just wanted to very quickly introduce what is a traditional supply chain. So we're thinking about Amazon, a big manufacturing facility, and we try to come up with the optimal network, the optimal supply chain to deliver goods to the customers. And some of the assumptions in most of these problems is that we know what are the raw materials, we know what we need to make our product. The raw materials are sourced from a point, a facility of our vendor. The quality is relatively constant, that's ensured by our vendor, and we have already know how we are going to deliver these materials. So a distribution center would be in a city, right? Biofuel supply chains are quite different. Here is using real data from Michigan. Our collaborators were in Michigan, because it's geographically distributed. The raw material is geographically highly distributed. One thing, it varies with time. We had a drought year, or we had a year that the weather was somehow different. The yields are going to be very different. The lands, we don't know yet which of these lands we're going to use, because these crops have not been established, and really here our goal is to understand these systems, right? And as I already said, there is a lot of variability in our feedstock. So this is a feature, the geographically distributed nature of the primary resource, not only in the area of biofuels, but this is a map with solar irradiance, similar picture for wind energy. So in order to get a better understanding about the systems, I would argue that we have to take into account land availability and crop productivity, then go to biorefinery design, which I have already discussed, and then put everything like in a network, regional, very large scale network, and try to understand the systems. So we are very lucky we collaborate with some colleagues from the University of Wisconsin and Michigan State University that help us gather all this data and then plug it into our models. So in land availability, the question is, what is marginal? It's a term that is not used very widely these days. Bioenergy land, bioenergy appropriate land is another term. But these are all different types of lands, formerly irrigated, conservation lands, that can potentially be used for biomass. And there is this kind of simplified graphic that says, if we have a very high quality land, then probably want to use it for food. As the quality of the land deteriorates, at some point we would like to use it for bioenergy, and then finally just grazing. But these threshold values are very kind of difficult to establish, and they will change with time. With less rain or more rain in other parts of the country, these thresholds are going to be changing. So what our collaborators did, was to try to identify marginal land using these different definitions of marginality, using satellite data. So these are collaborators, and this is finally what is a historically abandoned land at a 30 by 30 meter resolution using drones. This is kind of the picture. And the color here will indicate what's the potential yield, I think. They did the same for formerly irrigated lands. Here I just wanted to show this, that it's, again, that's the imagery, and it's kind of very clear that it was formerly irrigated. They have temperature sensors that they can see during irrigation season, whether it is still irrigated or not, and then they have this imagery and they can identify these lands. All this information sits in this very nice tool. It's called atlasglbrc.org, where you can go pick different options, like what type of land and some other things here, years of abandonment, and it will automatically return the lands that can be used. Then this becomes input to these models that basically try, and I know a little bit, but again, it's not what we did in the group. Our collaborators at MSU have done that, where given weather data applied in these lands that I have identified, then they can predict these models' productivity, so that would be kilograms per hectare or tons per hectare, and some other outcomes, for example, soil sequestration potential. So it is a nice analogy with engineering, but I'll skip it due to time constraints. So this is now the map, again, that we can use. This is the yield in this region of 10 states in the Midwest, generated from our collaborators at MSU. Okay, so now, just the big picture. We have the crop simulation data that is going to give us, this is for Wisconsin, crop simulation data. So we will have the information about productivity and sequestration potential. Then we are going to have some information about potential locations of biorefineries. And then what I have already discussed, this would go into an optimization. We will obtain some results. That's not very interesting. We were very happy when we did it. That is maybe 4 or 5 years ago. But at that point, we could only study systems up to a state. So it's kind of a little bit not very interesting solution. There is a refinery installed in Madison, or that would be the kind of the idea, the optimal, with some depots spread around the state. Very small demand, we were considering. But now this ignores completely that Iowa actually has very fertile lands. And if we had included Iowa, it would be completely different. So the reviewers, many people kind of complained. They said, no, if you want to get meaningful insights, you would have to go to regional, at least regional scale, because then we would see the interactions. It's a very arbitrary, the boundary that we have drawn here, and say, find the optimal solution for this system. So that's what we did. So same people involved, we just did the calculations for larger systems. So this is the 8th state in the US Midwest using, again, real data. Real in the sense identified, the candidate lands identified using drones, the calculations for productivity and soil sequestration done using these models of the agronomists. So this is the potential for carbon sequestration. So bluer regions have higher potential. This is the yield. Bluer regions have higher yield per square kilometer. So that was one. And then we added on top of that some other information. So these are all the locations, the dots for injection. So based on some renewable energy, National Lab for Renewable Energy, they have identified some locations for sequestration. So these would be the different locations. And then we pre-calculated if we were to install, let's say, a biorefinery here, which location would we pick? It's not immediately trivial because these locations have very different costs for sequestering. But we did that calculation beforehand, and now we were able to include these sequestration sites. And then the other kind of thing that was not included earlier, because we were focusing on ethanol, whereas now we are considering all the technologies, is electricity grid. If we are producing electricity, then it is very important to see what electricity are we displacing. So in dirty, let's say in states where the mix is less renewable, it would be beneficial to use biomass to produce electricity. In states where the mix is already quite renewable, then maybe producing something else would be better. So emissions and costs, and then these are the results, or the types of results that we could obtain. So now we see actually that we do not install, I don't think, this might be Illinois and Wisconsin kind of state line. So this would be the refineries that we would employ, and we would use pyrolysis. But this is when we do not account for the social cost of carbon. Big discussion, we can discuss that later in the Q&A. So this assumption basically says we will get the credit from the Inflation Reduction Act only, which is what happens at the biorefinery, right? If we are capturing CO2, we get that credit. What happens if we choose to plant our biomass in a field that is going to sequester in the ground more carbon. We don't get any credit today for that. There is no way to measure and then get that credit, right? Or what about the avoided emissions due to transportation? If we make the choice to source biomass from closer in the biorefinery, we won't get any credit for that. So this next analysis values CO2 the same way, regardless of whether we get the credit or we don't, but it's still, we are mitigating CO2. And actually the solution is very different. So the block colors, the outline, indicates the technologies that we pick. And we pick very different technologies. And even the configuration of the supply chain is very different. Okay. What we see also is that, for example, gasification, these two colors are chosen in areas where you have very high yield. The reason for that is that gasification are technologies that benefit tremendously from economies of scale. So we wouldn't want to have a gasification facility in an area where it doesn't have high productivity, because this would mean that we would have to go very far away to collect the necessary biomass to have a large facility. So we choose to install gasification systems here, but very different technologies elsewhere. And then again, we produce electricity based on the mix in that state. Okay, so in the last few minutes, I'd like to talk about something very different, electrification. That's something that we have become more and more interested in the last couple of years. It's about electrification, industrial electrification. And I think I'll go very quickly through this slide. These are different projections of the availability of electricity through 2050. Based on some optimistic projections, we'll have a lot of electricity. That naturally leads to the question, how can we use this electricity in addition to electrifying transportation sector? A lot of research has gone in this area. People are starting to ask, how can we electrify this pie of the energy pie, right? Transportation, we are moving in this direction, but also manufacturing. That's how manufacturing is subdivided. Can we electrify? And there are studies that are asking these questions, but we would like to develop a general framework. So this is the question that we are trying to address. Let's assume that we have a system, the details are not important. We have a process, we call it, P1, and that's what we do today. It requires red electricity, but also requires a lot of heating. Steel manufacturing, cement manufacturing would be these big sectors that fit this description. The first question is, when would it make sense to use electricity to meet this heating requirement? Today, probably is not a good idea, but maybe it will become a better idea in the future. So when should we be switching, basically using electricity instead of natural gas for heating? And then another question, more interesting, is if we can come up with a new technology that fundamentally requires much more electricity than heat, as opposed to the first technology, when would we employ this technology? These are the processes and these are the questions. Now, so far, we have assumed, and actually that's what we have been doing in the discipline traditionally, that once these systems are built, operate as what we call steady state. They do the same thing all the time. But now, as the electricity grid is renewable at a certain time of the day and less renewable, we will have to start thinking also about flexible operation. Okay? So, kind of these are the 6 alternatives that we will be using. Traditional process, when do we switch to use electricity only? When do we switch to a new technology? If we operate in steady state, or all of these 3, we have the ability, which requires bigger capital investment, to operate them flexibly. Okay, so and I will be using this notation. I think I'm going to drop, just show here sample results. This is what we do today. We have a certain capacity, and this is the energy that we are consuming. Some of it comes from natural gas, some of it comes from the grid. once we have built the system, we have made a big capital investment, we want to operate it at this point all the time. But now, if the electricity price varies significantly and how renewable electricity is varies also significantly, we may want to make a slightly bigger investment and not operate this system at full capacity when electricity is very dirty or very expensive. So there is again a kind of trade-off between operation and design. And this would be if we switch, we don't use we use more electricity and okay, so same idea, heat map, every point represents the result of a single optimization. We are asking the question here, how good should be the new technology? This is the relative emission factor. How much electricity versus natural gas we need. So this is the efficiency of converting electricity to heat on this axis. These are two very important parameters. The answer depends on where we are in the country and of course in the world, because the electricity that we're using is going to be very different. So if this white line represents, let's say, the threshold for switching from the old technology to the new technology, depending on where we are and this efficiency, the switch is going to happen at a very different combinations, right? So if we want to, let's say, provide heat at 120 degrees, this efficiency is going to be very high or very low. So depending on what are the specifics of this, what is the relative efficiency of the new process with respect to the first, that's this, and this is where we are. So that's the answer, and I'll skip that. Second to last slide, this now is the same kind of analysis, but now we're considering flexible operation. We allow the new process to be less than at full capacity. And what we see here is the relative cost savings if we allow this flexible operation. And what was very surprising, and in some ways a little bit different from some papers in the literature, is that the benefit is not that large, actually. The benefit from flexible operation is very few percentage points, 4%, 5%, which again was surprising. I'll skip this too because I'm running out of time. This is the last slide with results. When I motivated this work, I said we would like to have a general framework. Right, a general framework that would allow us to address this type of questions. And here is one example. So these generic blocks that I described, P1 and P2, how we do things today is P1, how we would do things in the future is P2. We applied that for ammonia. So ammonia has very large energy demand, one of the most important processes. This is how it's done today. It's steam methane reforming, so we use natural gas plus Haber-Bosch, this famous reaction, and we operate it at steady state. What would be the alternative? We use electrolysis to get hydrogen necessary for ammonia, and then electrified Haber-Bosch. And we have flexibility, operational flexibility, but we cannot turn it off completely. We can go down to 10%. So this is now what changed, how the electricity price would have to be reduced and what would be the reduction in the emissions to transition to the new technology, the electrified technology. This is a comparison, again, change in electricity emissions. This is business today. We have these emissions per kilogram per ton of production of ammonia. This would be the electrified process, significantly better. What was very interesting though was, this would be the electrified process. So as the electric grid becomes more green, the emissions drop. What was surprising is that producing ammonia the way we do it today and then capturing CO2 is actually very, very competitive. That would be the emissions of this technology. So what's the main point here is that the electric grid would have to become significantly greener for the new system, the electrified counterpart, let's say, to become better than current ammonia production plus carbon capture. So, just some concluding remarks. I hope I was able to convince you that systems engineering in many ways allow us to study these systems. And what I would say, I'm often get asked, yeah, but are we ready to do it? Or can we do it? Or I think it's understanding, right? What I would argue is that allow us to understand the systems and the trade-offs. I talked about these three different systems. These are the main takeaways: location-specific in terms of BECCS, location and time-dependent, and then the electrification. What was interesting is really that now we have to account for design and operations, these two scales that I mentioned at the beginning, at the same time. There are many challenges that we haven't addressed. Deep uncertainty is one of them. What are going to be the credits, going to the question in 10 years or 15 years. There's a lot of uncertainty about the number, but also about the probability of a credit, seeing a credit. How do we solve these systems? Again, it's an open challenge, so work on the optimization side of things is very interesting. And then some really final thoughts. One challenge is also how to get these models from limited experimental results, use of real data, and that's why I'm affiliated now with HMEI, and I would be eager to work with people who really can help us get this real data. And then finally, as I said, collaborations with experts is critical. So thank you very much, and I'll be happy to take any questions.
All right. So for those of you on Zoom, I'm monitoring over here questions on Zoom. For those of you in the audience, the first question will come from a student or a postdoc. So wait, let's wait for the microphone so that the people on Zoom can hear the question.
All right, I think this works. Thank you so much for the super interesting talk. I'm just wondering, for the electrified Haber-Bosch ammonia production, did you look at islanded systems where you can stack all the Inflation Reduction Act incentives? Like if you build your own solar, wind, and battery storage, you stack all of that together. If that changed the economics and if it's more attractive that way?
So short answer, no. We are thinking about it, including battery or other forms of storage to allow us to have more fixed operation. That would also increase the cost to have, let's say, our own PV system to supply electricity. It would increase the cost if we have batteries. So it's the same type of trade-offs, but maybe the results would be different. Thanks.
Thank you.
Two questions near each other. So 1, 2.
Thanks so much. The question about the map with the yield for bioenergy. So I was kind of interested because it went very quickly, but it looked like it was monotonically decreasing or increasing as you went sort of southwest. So I was curious about, maybe it's the shading of the colors I didn't understand. It looked like the yield was sort of there were gradations as you went along the map. So I was curious, that seemed to be, I would have thought there was more heterogeneity.
Not necessarily. If I remember well, I think there are some, let's say, very, very fertile lands in Iowa and then in Indiana, but not necessarily, I wouldn't say it's a monotone decrease.
Okay.
Maybe overall the trend is like this. Definitely northern Minnesota and Wisconsin, they are not very fertile, but I wouldn't say it's
Okay.
uniform. Yeah.
Thanks.
So just wanted to, prior to this one, I'm going to interject a question. So to what extent did that reflect, those gradients in production reflect a quality of the soil versus a quality of rainfall, temperature, et cetera? Is there atmospheric? Both. Okay.
So both. So actually, it's very, very interesting point. So our collaborators who are generating the productivity numbers, we have been discussing about that, and they say actually, climate change is one area where can be beneficial in these maps because average temperatures would be higher, further north, and potentially there may be more rain. So it's both the soil and then weather data that they use to do these calculations. And they have done some of these calculations for some, let's say, future potential realizations of weather data. And they find that further north, again, it's not maybe, varieties of certain crops that cannot grow today could potentially, and they are more productive, could potentially be grown in the future. So it's a very, very interesting kind of dynamic and trade-offs.
Thank you very much. I also have a question to this regional study you showed. And I was wondering when you would include agrivoltaics, so the combined use of land with photovoltaics and using crops, when you would include this, and then maybe optimize for minimum cost, maximum energy yield. How would you think would this change your analysis?
Sorry, but I didn't catch the first part. So
when you would include agrivoltaics, so the combined use of photovoltaics and growing crops on land.
Yeah, so if we could use photovoltaics to provide energy in the biorefinery or independently? Independently use the same land to provide both biomass and power. Is it the second?
Or in general, I think it can be used for both, you know, we just would have in addition, or another thing, you know, what people now are considering, you know, having photovoltaics on land, but then just grow whatever grows there, which is better for insects. But anyway, often, as far as I heard, has a higher energy generation per area than with plants, for example.
So, and there is Rakesh Agrawal at Purdue that has kind of thought of this idea. I think this would partially address the challenge of space, right? But I don't think that it would change, again, if renewable power is not used in the biorefinery, I don't think that it would dramatically change these results, right? In addition, we will get the additional benefit of having more area to install photovoltaics. I'm a little bit hesitant. It could change it, but I don't know in which ways. If, let's say, we decide to establish very large areas with bioenergy crops and PVs, establishing these PVs could potentially change the electricity mix regionally, which could potentially change the optimal biorefinery technology. So if we don't have these PVs, maybe with an example, if we don't have these PVs, using biomass to make electricity makes a lot of sense, right? We don't have emissions when we burn hydrogen. We don't have emissions when we burn electricity. So if we use biomass to replace electricity coming from a dirty grid, that's the best option. If now we install all these PVs and we meaningfully change the grid, then the biorefinery would no longer be producing, it wouldn't be optimal to produce electricity because the electricity is already very good. So that would be maybe one way that would change the results, but it would have to be in a very large scale, right?
So we have a question here, and as the microphone gets, I have a question regarding the optimization. So you're optimizing for maybe cost, value, profit. Would the structure change if you design for reliability to disturbances, right? I'm thinking right now, Helen just knocked most of the Southwest power, or much of the Southwest power out, or Southeast power out. If you designed for reliability, how would this be different?
So the structure, so there is this kind of field that is called optimization under uncertainty. Yeah. In this large field, sometimes we say we optimize for the average or for the worst case, right? So there are kind of different ways to account for these events. So if we were optimizing for reliability, I would say maybe two things. We can formulate these models, we can do it conceptually. The computation would be much more expensive because we'll have to account for all these probabilities, right? And what qualifies as a Helen? Is it like a 2% probability, a 5% probability? And so in principle, it can be done. I don't know about computationally for this type of size of region. we have done it for significantly smaller systems, and the cost goes up. Usually, there is this trade-off, right? As our systems become more reliable, we have to over-design them in some ways. They will be more expensive, but then we don't have the catastrophic event where everything fails, and that's also expensive.
Thanks for the great talk. Can you maybe expand a little bit on the boundaries of the system that you're considering? In particular, multiple of the processes you discussed end up in storage. And so how would that change the entire calculus if you were to assume a limit on what can be stored and at what rate?
So the boundary in which, you mean the geographical boundary or the boundary of the processes and
Of the system.
of the system?
So basically, your process ends with storage, but storage doesn't seem to be part of the system.
So ends up, so we include these potential locations for storage, and each one of these locations have a supply curve. So the more we store, the more expensive it becomes. But this is like what I would say an offline calculation that we took from the National Energy reports. So we haven't gone into geological, let's say, modeling of this. We have a very approximate representation of the storage sites. We know their location and the cost to sequester.
There's no like plausibility limits, scale limits.
Yes, we make
because of lots of these storage sites are prospective. They're not
yes.
active. They're not developed. So basically, your system sort of has an endpoint that just doesn't exist yet.
So again, we are not in in this field. We took the best available data that we could find, and the data that we found was that I completely agree that they are not explored, but they have been identified, I think, with capacities. And I think that the calculation that has been made is that as we increase the pressure, we store more and more, the cost is going to go up, right? So again, what we used in our representation is for each one of these potential sites, what's the transportation cost, and then what's the cost for injecting it. And we have a capacity, I think, to use up to 1% of its capacity per year. So we cannot pick the cheapest one and inject all the CO2 there. We would have, we say up, I think, 1 or 2% per year of its capacity.
Thank you.
We have 1, 2, 3.
Thanks, Christos, for the great talk. I'm actually following up from a discussion that we had about a year ago on the multi-stage formulation that you just showed bits of. And I'm wondering if you're still doing like a deterministic dynamic programming, if you have any plans of modeling the uncertainty, learning rates, things like that.
Very loaded. So for the very small example that I showed, the Wisconsin kind of, we did stochastic programming. For the regional system, but that's a snapshot, so no technologies, no learning. We have done deterministic. We are thinking now to take maybe in 3 directions, kind of expand this work in 3 directions. One is have learning curves, but at a very coarse level, and even uncertainty in learning with a tradition like as a capacity, as a function of capacity. So that's one direction. Trying to do the deterministic at a national level would be the second one. And then uncertainty, but I haven't mentioned uncertainty potentially, but yeah.
And how have you done the uncertainty quantification of the Wisconsin, like for the investment materials or?
Yes. So we focused, because we have data from our collaborators for 10 different years, so yields, soil sequestration, so we focused on demand and yields. We could potentially have different capital costs, different The Wisconsin study was very limited because it was only about microbial conversion, which we probably will have a good understanding of costs. So again, but to answer the question, yields, sequestration potential, demand was the uncertain parameters we considered.
Hi, thank you for your talk. I noticed your analysis was very regionally focused on the Midwest, and I was wondering, especially since centers of energy demand are on the coasts of this country, whether the choice of a regional focus was based on where you had the best available data or the best collaborators in this case, or if, especially because the analysis is about bioenergy, that the bioenergy example, at least, is fundamentally relevant to the Midwest, where there's abundant farmland.
Yeah, so I would say that it's the two things that you identified. One is available marginal lands and biomass is mostly in the Midwest and then South. One. Second, the collaborators and the data that we had available at that point were in the Midwest. Now, as I said, we are trying to expand to the entire nation. We have the land availability data, but so from the UW collaborators, our MSU collaborators have not run their models to generate productivity data for the rest of the country. I will make also one point, given all the costs for transportation, because it's so biomass has a lot of water. When we ship it, it has a lot of water and it has a lot of volume, very low density. So compared to this transportation cost, shipping the final product to the costs would be negligible.
Thank you. And I have a question up.
Thanks for the talk. I have a question about your ammonia production example at the end. You showed that the grid needs to be very clean for the electrification case to be cleaner than the traditional plus CCS case. Given that over the time frame of a plant that's built in the next 5 or 10 years will certainly take us through to a point where the grid is going to be, maybe near 100%, 95% clean. How would a corporation think about how to optimize what they build right now between those two options? You're potentially losing something now in terms of emissions with a less clean grid, but then in 15 years' time you're actually getting an advantage from the clean grid.
I'll say what I've heard in a couple of conferences where people from industry are. I think the biggest kind of driver, but also fear, is the incentives. So I think the incentives can because here I was showing just emissions right now. Whether a company would move with a new technology, I think they will think about economics, right? I think they will think about the financial aspect of it. And I think incentives could change that in one way or the other. I think the uncertainty about the incentives is what maybe gives them some pause. That's, I think, what I would say, again, based on discussions I have had with them.
Raj, you can get.
Thanks. I guess my question is on the electrification part. I think a lot of the analysis you show, including using the e-grid data, I guess I have always been wondering, do you think it makes sense to have a electricity carbon intensity data on a more granular basis, because e-grid regions are usually pretty large, comparable to your state size? For example, if a project uses their off the meter renewables, or maybe just their local grid is cleaner than the e-grid, what the e-grid data shows, do you think it makes sense to have this kind of data into the analysis?
Yes, so I think maybe I'm thinking about there are 3 ways to address this, right? I think given a microgrid, and if we can kind of certify its footprint, which might be difficult, right, in the big grid, but then we would place it on this axis, right, and we would get our answer, right? I think batteries, if they are included in this microgrid, would change the calculations quite a bit. Not that the methodology would be the same, the framework would be the same, but the findings can be different. Because then I think we have thought a little bit about that. It becomes a question of, is it more important to build one unit of extra capacity for the actual process? If we do that, we can lower our production when electricity is expensive or not renewable, or the equivalent amount of batteries. Then we keep constant our production at the maximum. So it's going to be a little bit of a trade-off between these two. And I don't know which way it would go. We would have to do the analysis. So we would repeat the analysis with some options like this, these additional options.
Okay. Looking at the time, I think we're going to have to thank Christos again. Thank you, Christos, for a great presentation. So I think having this systems view as we work in this energy transition is going to be crucial to have the right approach. The trade-offs are inherent in everything here. Now, I just want to remind you that Tuesday, November 5th, we will have our second speaker for the fall. It will be Professor Christina Reel from Ecology and Evolutionary Biology, who will be talking about biology and conservation of tropical birds, linking life history and ecology. So look forward to seeing you all there. All right.
Thank you.